Welcome back. I'm going to go ahead and take a look at that overall transformation again, and we're going to go ahead and come up with this TTT diagram. The reaction that we're going to be looking at here is the eutectoid reaction, or the formation of pearlite, as I go from austenite down into pearlite, formed of this ferrite and cementite layered structure. All right, so the one thing that we're going to have on our curve, we're just going to remember here, 727 is where I have to go below in order to form the pearlite. Okay, so here is my transformation curve, just one transformation curve at 675. So again, this is an experimentally determined curve following the Avrami equation. And what I'd like to do is, instead of having a whole bunch of these curves at all different temperatures for my system, I'd like to come up with one diagram that helps me to see the whole system, and I can make some predictions relatively easily. So what we're going to do is we're going to come here at 675 degrees. So here is 675. And what I want to plot now on a time axis is simply the start of the transformation. So that's nucleation. The 50% line, 1 over the time for this 50% is often used as the rate of transformation. And then I want to use the 100% transformation. And I'm just going to plot those 3 points on my temperature versus time plot. Okay, so I've turned one of those S-shaped curves, Avrami curves, into 3 points on my plot. So if I raise the temperature to 700 degrees C, and I do that again, then I'm going to get a point like this, maybe one out here somewhere, and I guess way out there. I need to try and see, make sure I made a straight line there. If I drop to 600 degrees C, then I'm going to get these 3 points. And so if I keep doing that with my data, you can see that I can then go ahead and connect them. And I'm going to form a line. The first line here represents the 0%, that is the start. The middle line will represent 50% completion. And then once I cross this green line, or this line here all the way to the right, I will get 100% transformation. So now I can look at curves rather than individual S-shapes, so I don't have to do any interpolation. It's all here for me. Now, we're going to go ahead and consider this case where I'm going to drop my temperature to 620 C, and I'm going to hold for some time. So the steps here, or let's go ahead and austenitize, is the first step. And austenitize just means that I'm going to hold my temperature above 727 degrees C, which we know from the phase diagram puts us into the austenite region. So I'm going to austenitize as step 1, just means I start here as austenite. Right? So it doesn't matter the time, everything up in this region, if I just stay up here, is austenite. So at my time t equals 0, that's my starting point for our transformation, so austenitize. All right, then it says to go ahead and drop the temperature to 620. So we're going to just assume that this is basically an instant rapid cool. And in fact, the way we're going to interpret things, we really just dropped it instantaneously down to 620 degrees C. And then from that point, we held at 620. So there's my time axis now moving along. And we held until we got to 100 seconds. And so that would be this point here. And then after that point, we can't stay there, right? Otherwise we'd still be holding. So we're going to drop then down to room temperature. So that's what my process would look like on this plot, on this curve. And now let's see what happens. So as I hold at 620, at somewhere around about like 2 seconds or so, it looks like, I start forming pearlite. And so this region over here is still austenite, and this region over here is the ferrite plus cementite pearlite microstructure. So I start the transformation here after about 2 seconds. I'm 50% completed after about 6 seconds or so. And then after about 10 seconds, I've actually fully formed 100% pearlite structure. I have no more austenite left. This would be my diagram, my picture of it. You can see the layered structures. There's no proeutectoid phases in here. There's no ferrite or cementite as a proeutectoid because this diagram, the way that it is for a 0.76 weight percent carbon steel. So we're exactly on the eutectoid composition. All right, but that would be my structure, and it tells me what I'd have to do. So if I wanted to get this pearlite, I just simply need to do a 620-degree hold for 10 seconds, 100 seconds, sorry. So, and actually I only need to be at 10 seconds to actually fully form it. All right, so that's kind of how we would use this to predict what is going on. So we'll keep going and use this a little bit more. There's a little more information we could pull out of this. If we were to do a higher temperature transformation on that diagram versus a lower temperature, then the higher temperature one takes longer for the transformation, so it's a longer transformation time-wise. The lower temperature one is a very short time scale transformation. And the net result is I still have pearlite in both structures, but the longer transformation, since it has more time for diffusion to occur, I end up with a more coarse structure, larger spacing between my sheets of cementite. Where at a lower temperature in the short time, I'm going to end up with a much finer structure. And so that's again what we're seeing over in this case. So we could talk about there being a coarse versus a fine structure. And the reason why we care is that this fine structure is going to have a much higher yield strength, tensile strength, but of course lower ductility than the coarse structure. So we're already seeing one way in which we can control properties even within pearlite just by forming different length scales. Both of these have the same overall weight fraction of cementite and ferrite because they're both exactly the same 0.76 composition. All right, and that's what the diagram's trying to show. If we're a little lower in temperature and do it down here, things happen very fast. It's fine. And if we're up here somewhere where things are occurring, much more slowly, then we have coarse. Now we don't have really a line that goes through here where we say above's coarse, below's fine. It's really, very fine here, down here, and as we go further and further up this way, it's becoming more and more coarse. But in terms of our class, if asked, you can imagine there being a line somewhere in the middle here. And if you need to identify fine versus coarse, then you'll either be put up on this end of the diagram or down this end. It won't be put smack in the middle, for example. All right, so that is, again, this is called our TTT diagram. And if we were to keep going, here we go, I don't know what happened there. If we keep going on the diagram, we can get the rest of it. We only did up till about here. If we keep going lower, what we will find is at some point here, we have actually gotten at the peak of that overall transformation rate that we saw before. And now as we lower the temperature even further, instead of this transformation occurring even more quickly, it actually starts to take a longer time again, and the curve starts shifting back this way. Now this is the case where the diffusion is becoming slow, and it's limiting our ability to transform. And in this particular case as well, when we start limiting the diffusion that way, the system changes from a layered structure to a new one that is more needle-like. And so this needle-like structure is referred to as Bainite to distinguish it from the layered Pearlite structures. And Bainite, being a even finer structure than the Pearlite, now is going to also have higher strengths. But otherwise, we can do this the same way. If we were to hold at 400 and we held for at least 100 seconds, then we would have 100% Bainite. Right. Then if we keep going in the diagram, and we don't, upon cooling, we don't actually cross this red line at any point. So I could do that if I was to cool very, very rapidly. Now I'm going to get so low in temperature that I've essentially shut off diffusion altogether. And so I've frozen in my austenite structure, but this system has so much strain in it that the austenite will transform, but without diffusion. And so this is like a displacement transform. We're just going to shift atoms, but we're not actually diffusing them. And it forms something called Martensite. And we'll look at Martensite in a second. Martensite is extremely strong, but it's also highly brittle. But it's a very important structure to get on our way to get something called tempered Martensite, which is quite nice for steel, for things like knife blades and those sorts of things. All right, Bainite, just trying to show you that needle-like structure with the cementite layers inside of these sort of needles. The Martensite structure, we said it's just a distortion in the lattice. So austenite, you recall, is a face-centered structure. And then when we shift down into this Martensite, it transforms into body-centered tetragonal. So remember that tetragonal means that I stretch one axis. And so this stretched axis is the location where the carbons can sit, so I can fit more carbons in the lattice. But they're in there and they stretch that, that C axis, forming body-centered tetragonal. All right, so what we're going to do, I'm going to take a little break here. And when we come back, we're going to take a look at this diagram, this TTT diagram, and we're going to see how to form some various microstructures and how to come up with some different processing routes to get some various microstructures.